All right, we're going to go through some of the example problems from the standard plate count and the concept of serial dilutions. So I've got 6 problems here. We're going to start with some basic original cell density, showing you how to use the equation and the formula to calculate original cell density. Then we're going to go into some basic dilution problems. We're going to do serial dilution, and then the last problem we're going to do involves both serial dilution and the standard plate count. So let's get started. Our first problem is one of the basic original cell density problems. It says a bacterial culture is diluted down to a concentration of 0.00001. First thing, always keep track of the zeros, and that is an exponent 10 to the negative fifth. So it didn't say exactly how many steps, but as a visual here, that would have been done over a series of steps, getting us down to a low concentration, 10 to the negative fifth. And next it says 1 ml is plated onto a petri dish, and after 48 hours of incubation, 115 CFUs or colonies are counted. So the question then becomes, what is the original cell density, the OCD of the original bacterial culture? So our equation for solving this is OCD is equal to CFUs divided by D times V, D being the concentration, V being the volume plated onto the actual counted petri dish. So wherever these CFUs come from, the volume that went onto that plate is our V. So what I like to do is just to keep things in order, write out the variables to the side. They're in the problem, but go ahead and just, whenever you're working a problem like this, just write them down redundantly, just so that you have them nice and clearly separated and you're not going to just glance in the wrong direction as you're going back into the problem. It helps your brain stay organized. So write those down. Now what we're going to do is we're just going to take the variables here and put them into this equation. So 115 and the units for CFUs are CFUs, so it's a redundant unit. The D value has no units, it's just a decimal. And then we're going to put that in parentheses with our volume next to that, which has units of units of milliliters. So we have 1 milliliter. Next, what you want to do is multiply out the bottom units so that you don't try to do this in one step. So we're going to take the D value, multiply that by the V value, and then carry that over to the next step. Now this happens to be anything times 1 being the same number, so the number doesn't change here, but now we have the product of this multiplication, and now we're just going to divide that into 115. Okay, so we're going to divide 115 by 0.00001, and that becomes 11.5 million CFUs per ml, and the units are CFUs per ml. So whenever we write this out, the standard units, CFUs per ml. All right, take a second to rewind that if you need to, and we'll go on to the next one. Similar problem. The culture is diluted down to a concentration of 10 to the negative fourth in this case, 0.0001. Forgot to do the formatting there, but that's 10 to the negative fourth. We played out 0.1 mLs, and after 48 hours, we count 81 CFUs. So once again, what's the original cell density? Write out the variables to the side. All right, put those variables into the equation. 81 over D times V. Now, multiply the bottom, the D times the V, and the product of that is now a smaller number, 0.00001 ml. Carry the volume over, and now we divide 81 by 0.00001, and we get, in this case, 8.1 million CFUs per ml. The units again being CFUs per ml. All right, so rewind these two if you need to go back over these, but these are pretty straightforward. It's just a matter of getting the proper equation, identifying the variables, putting them into the equation, and then just making sure you don't skip too many steps to get the equation wrong. So do the bottom part first, get the product of the bottom two numbers, and then divide that into the top number, and you should get it right every time, as long as you don't type in the wrong number, fumble into the calculator. All right, next question. This is a basic dilution question. So we're just doing a one-part dilution. So it says you buy hydrogen peroxide H2O2 at a concentration of 35%. However, you need a 3% concentration. Calculate how to make 500 milliliters of a 3% solution. So we start here, but we want to make 500 mLs of a 3% solution. So how do we do that? The equation for any type of dilution problem is going to be the D1 V1 equals D2 V2 equation. And what this equation is going to tell us, is how to rearrange the variables between two solutions to come up with a desired value. Now, as long as we're working with the same solution, hydrogen peroxide, in this case, the equation here can tell us how to take 35%, which is our starting concentration, D1, and manipulate that into a final ending concentration, which in this case is 3%, D2. And then in order to do the concentration differences, we have to take into account volume. Volume and concentration are directly related, and that's what this equation is telling us. So D1 is the value for the starting concentration. And it's expressed as a percent, but when it goes into the equation, we want to convert that to a decimal. So take the percent, divide it by 100, or move the decimal place 2 units to the left, and D1 will become 0.35, and that's what will go into the equation. D2 is our 3%. Once again, divide by 100, and we're going to get 0.03. V2 is 500 mLs. V2 is the final volume that we're going to end up with, in this case 500 mLs. Now, whenever we're doing an equation like this, we're going to need to have 3 of the 4 variables and solve for the 4th. So what you want to do is start by identifying the 3 variables that you know. And if you don't know, just start writing them out based upon how you see the problem. So the starting in concentration and the ending concentration are given, and then the total volume, how to make 500 mLs as our total volume, is also given to us as well. So what that means is that we actually don't know the V1, which is how much of this initial 35% do we need to use. So the question actually becomes, how much of this do we want to transfer in order to make this dilution? Because we only need a small amount of this. We're going to be reducing the concentration, and we're going to be diluting it with water. So we only need a small amount of the starting concentration. So the question becomes, how much of that do we need to make 500 mLs? Okay, and I'll explain further as we go here. So the equation we're going to use is the D1 V1 equals D2 V2, but what we want to do is we want to rearrange that now to solve for the missing variable that we need to know, which is V1. So what we're going to do is we're going to take this left side of the equation and divide it by D1, and that's going to cancel out the D1 from that side. And then to rebalance that equation, we're going to follow that over on the right side. So we're going to end up with V1 is equal to D2 V2 over D1. And now we've got that equation rearranged in the form that makes sense to solve for the V1 variable. Next thing we're going to do is we're going to bring down the variables that we wrote out into the equation. And I think it's probably more important in these equations, in these problems, to write these out so that we can put them into the equation correctly. If you have to go back into the problem and then change the decimal, you're more likely to make a mistake. It's not that you can't do it, you're just more likely to make a mistake. So write those out, and then now they're just easily input into the equation. So we got 0.03 D2, 500 mL V2, and 0.35 is D1. Now once again, what you want to do is multiply the top numbers and get the product of that. 0.03 times 500 is 15, and then divide by 0.35. Do it in 2 steps, and 15 divided by 0.35 is going to give us 42.9. I'm actually rounding up there. It's going to be 42.857, I believe. And what we want to do is we want to round it to the nearest tenth of a decimal. So I actually rounded that up to 42.9 mLs. Okay, so that's going to tell us how much we want to transfer to our solution here. Now, whenever we're making a solution, what we have to realize is we need a certain amount of the starting concentration. We've calculated how much that is at 42.9 mLs. What we also need then is a certain amount of water to top that off. And the combination of the water and the starting concentration, the volume of the starting concentration, in this case is going to need to equal exactly 500 mLs. So what we need to do next then is figure out how much water do we need exactly. And to do that, we just need to take the final volume and subtract that from the concentrated 35% that we transferred over. So the difference between how much we're going to end up with and the amount of the starting concentration we used is going to tell us how much water we need to get exactly 500 mLs. So we just take the final volume, B2, 500 mLs, and we subtract that from our V1, the volume transferred. The difference is the exact amount of water. In this case, 457.1 mLs of water. So when we add the 457.1 mLs of water to the 42.9 mLs of 35% hydrogen peroxide, we get exactly 500 mLs of a 3% hydrogen peroxide. And that is how we do it. Now, one of the things I'm going to typically ask you in the homework and on the quizzes is explain or tell me how you make the dilution. You've done all the work here. The last thing is just put it into a sentence or put it into to wording that makes sense. And so you would say, in this case, add 42.9 mLs of 35% hydrogen peroxide, H2O2, you can write it out if you want, to 457.1 mLs of water to make 500 mLs of 3% H2O2. So that would be the way you'd explain it. So do the math and come up with the numbers, and then put it into a sentence that explains to me if I were reading directions on how to do this. You've done the math, put it in a sentence to explain to me, add this much to that much to make this much. All right, go back over that if you need to. Let's go to the next one here. We're going to do a very similar problem. In this case, your instructor gives you 50% hydrochloric acid, HCl, and asks you to make 100 mLs of a 5%. Calculate how to make the dilution. So we're going from 50% to 5%, and in this case, we're going to make 100 mLs. We're going to use the same equation. We're going to write out those variables again off to the side. So we're starting with the 50%, move the decimal, divide by 100, we got 0.5, and we're going to make a 5%, we're going to have a 0.5. We're going to make 100 mLs. Once again, the question is, what is V1? How much to transfer? So it's the same kind of problem we just did last time. I'm going to go a little faster, by the way. Rearrange the equation, just like we did before. V1 is equal to D2V2 over D1. Put those variables into the equation. 0.5 times 100 over 0.5. Multiply the top numbers to get the product, 5 mLs in this case. Divide by 0.5. 5 mLs divided by 0.5 is 10 mLs. So our V1 is 10 mLs. We know how much then of the starting concentration we're going to need. But again, the final volume, 100 mLs, also includes water. So we need to know how much water. In this case, the math is a little easier. The final volume, V2 minus V1, is 100 minus the 10, and that's going to give us 90 mLs of water. So when we add 90 mLs of water to 10 mLs of 50% hydrochloric acid, we get 100 mLs of a 5% hydrochloric acid. The explanation there, add 10 mLs of 50% hydrochloric acid to 90 mLs of water to make 100 mLs of 5% hydrochloric acid, HCl. All right, I'm going to move on. Rewind if you need to go back over that. This next one is a two-part dilution, a basic serial dilution. So we're going to make a dilution of a dilution. So in this one it says starting with the 50% glucose, you add 1 ml of 50% glucose to 9 mLs of water, diluent. And that's going to give us our first dilution. Notice it doesn't tell you what the dilution is in this case, or how concentrated or how dilute. It just says that here's what you did. After thoroughly mixing, we now add another ml of the diluted glucose to another ml of water. So we're making a second dilution, dilution number 2. The question then becomes, what is the concentration, or the D, of the second dilution? So in order to do these equations, in order to solve this problem, we're going to use the same equation. And we're going to use the same D1 V1 equals D2 V2. The difference is we're actually going to use it twice. So we're going to use it in the first part of the problem to calculate our first dilution. Then we're going to take the result, or the product of that first dilution, and we're going to use that, and we're going to reset the equation and solve for the second dilution using the same part of the equation here. Okay, so we're going to do this in one part to make the first dilution, and in the second part to make the second dilution. So here's what we're going to do. We'll start it with just pretend we just have one dilution here. Start with step 1 to make dilution 1. So just like before, we're going to write out the variables based on what you know. These variables are going to be a little bit different than the last problems. So we know the starting concentration, 50%, is 0.5. We know in this case how much we transferred. It said to transfer 1 ml of 50%. So we actually know the variable for V1 in this case. We are going to know how much the V2 is, because what we're going to see here is that the V2 is going to be 9 mLs plus the 1 ml to give us 10 mLs. So with this one, what you have to recognize is V2 is equal to the amount transferred to the V1 plus the amount of water. So when we add the 1 to the 9, our final volume in that first dilution is going to be 10 mLs. So even though it doesn't say 10 mLs up here, when we add these two together, we have to realize that the final volume of this first dilution will be 10 mLs. So that's why V2 is equal to 10, the 1 plus the 9. What we don't know, what we need to figure out, is what is the actual concentration of this first dilution? What is the D2? How dilute does that become? So we're solving for D2 in this case. So just like before, we're going to rearrange the equation. In this case, we're going to remove V2 by dividing the right side of the equation by V2. So that's going to cancel out V2, and then we're going to divide the left side by V2. And then we can just flip it around so that we move the D2 on the left and the other variables on the right. So D2 is equal to D1 V1 over V2. All right, now with these variables here, we can put into that equation 0.5, 1 ml for V1, and the total volume for V2, 10 mLs. We're going to take 0.5 times 1, that's going to give us 0.5, and we're going to divide that by 10 to give us 0.5. So that means that the first the first dilution is going to be equal to 0.05. Okay, so we now know what the concentration here is, 0.5. The problem is asking us, however, what is the value of the second dilution? So what we're going to do now is we're going to take the same equation and we're going to reset it so that now the variables will apply between dilution 1 and dilution 2. So all the variables here now relate to D1 and V1, and all the variables here will now, the D2 and the V2 will relate to dilution number 2. Let me say that again. In the second part of the problem, D1 and V1 will relate to dilution number 1, and D2 and V2 will relate to dilution number 2. What we want to do is use the same formula with different variables now. So D1 is the starting point here for the second part of the problem. It is now 0.05. That was the answer from the previous problem. So we're going to put that now as our starting concentration. The problem is having us once again transfer 1 ml. And just like before, we're going to add that to 9 mLs, so we're going to get another 10 mLs here. So the question then becomes again, what now is the concentration of the second dilution, the D2 for the second part of the problem? So we're going to start the same way. We're going to take D2 and we're going to put these variables into the equation. So D1 is 0.5, V1 is 1 ml, and V2 is 10 mLs. Now, when we divide this, we're going to get 0.005. 0.005 is now the D value, the dilution or the concentration for the second dilution. So our dilution value for number 2 is a decimal will be 0.005, and if we want to convert that to a percentage, we would move the decimal place back 2 units to the right, multiply it by 100, and that would be 0.5%. I'm okay for my class writing out the variable either way, the answer either way. So you could say dilution number 2 is equal to 0.005, or you could say dilution number 2 is equal to 0.5%. Just make sure that you put the percent in the right place. So this is not 0.005%. It is 0.5%. So make sure you don't get that mixed up there. All right, so now we know that the dilution number 2 is the value that we see here. And that's it for this problem. We've done our work and we're done. All right, so stop and go back over that if you need to. Last problem here. Now what we're doing is we're taking a scenario where we're going to use the serial dilution and we're going to apply that to the original cell density that we did at the beginning. So let's read the question here. An undiluted bacterial culture, starting with an undiluted bacterial culture, you aseptically transfer 1 ml to a flask with 9 mLs of water. I forgot to put the 9 mLs here, but that's going to have 9 mLs of water in it. After thoroughly mixing, you transfer 1 ml of the diluted culture to a second flask with 9 mLs of water. After thoroughly mixing the second dilution, you plate 0.1 mLs of dilution number 2 onto a nutrient agar plate. After 48 hours in incubation, you count a total of 175 CFUs, colonies. What was the original cell density of the culture? So this problem is a lot like the very first ones we did. The difference is we don't have the dilution value, the D value, to go into the OCD equation. So we need to calculate the dilution value that went onto the plate. In the other problems, that value is given to you. Here you have to calculate that first. So what we need to do is a 2-part serial dilution to get the D value and then apply that to the actual number of CFUs. So what we're going to do is we're going to start with the dilution, and beginning with the starting culture here, we're going to do a 1-part dilution and then a 2nd-part dilution. So what we want to do is identify the variables that we know in our first dilution here. So this is going to be D1 and V1 here, and this is going to be D2 and V2 here. So take the equation, write out what you know. Now, one thing that's important to note is that when we start with an undiluted bacterial culture, the assumption is that the concentration is always 100%. So unless stated otherwise, given an undiluted culture, it is at 100% when you get it. Unlike other examples where the concentration starting was given, here it is assumed to be 100%. Nothing's been diluted. It's starting at the maximum. So D is therefore equal to 100%. Divide 100% by 100, and it's going to be a whole number in this case. D1 equals 1. We transfer 1 ml, and we're going to add that to 9 mLs, and so we're going to end up with another 10 mLs. So 1 plus the 9, I'm sorry I didn't write that out here for you to see that, but with that, 9 mLs was stated in the problem here. You'd have 1 plus 9 is equal to 10. Once again, we're trying to determine how dilute does that become in that process. So we're going to go back to our D1, V1 equals D2, V2, and rearrange that to solve for D2. And D2 is equal to D1, V1 over V2. Now we plug in the variables from our numbers set up here. D1 is equal to 1, V1 is equal to 1 ml, V2 is equal to 10. Now the units for ml are going to cancel out in this case. So mLs over mLs, that actually cancels out. So 1 times 1 is 1, divided by 10 is going to be 0.1, no units. So our variable, or our D2, for the first dilution is going to be equal to 0.1. Now we're going to take that and we're going to start again with the next part of the problem, starting here in the middle. So this is now going to be D1 and V1, and this is now going to be D2 and V2. So now D1 starting here is the answer from the previous problem, 0.1. Once again, we transferred 1 ml, and once again in the problem, we are transferring that to 9 mLs of water to make a total of 10 mLs. And again, solving for the D2 value. Rearrange the equation, placing the new variables in, we end up with 0.1 times 1 over 10 in this case. So 0.1 times 1 is 0.1, and divide that by 10, and we get now 0.01. Again, units cancel out. So now we know the dilution value for our dilution number 2, 0.01. Now what we can do is we can go back to the original cell density equation, putting in the variables for CFUs. Our volume in this case is the volume that was transferred to the Petri dish. And some people get this confused because there's lots of different volumes here, right? There's a handful of volume values. So how do you know which one to use for the OCD equation? You use the volume that was transferred directly to the plate. So 0.1 mLs, that came right out of the problem, right up here. So that was given to us. So as long as you understand that, you won't get that mixed up. Otherwise, it's easy to have a hard time understanding what volume goes there. So volume transferred to the plate, 0.1 mLs, that's our V value. And we had to calculate the D value. That's what we were doing in the first two steps. So that we now know is 0.1. So that variable goes here. And what we need to do is just do that in 2 steps. Take the product of 0.1 times 0.1, which is 0.001, and now divide that into 175. And our answer is 175,000 CFUs per ml. Just like we had in the beginning, it's CFUs per ml. So the problems I'll give you will be similar to this. It involves the serial dilution, and then it involves the original cell density, where typically you'll have to calculate the final dilution in order to solve for the original cell density. All right, one of the great things about the video is you can back it up, pause it, rewind it, as you well know. So make sure to do that if you need more time, and let me know if you have any questions. You guys have a great day.